Okay, hi Year 12s. I'm doing exercise 3G question 12. This is on page 91 of your books. We need to show that y equals b on a square root a squared minus x squared. Okay, now we're told that the equation for this ellipse shape, this is supposed to be a sports stadium by the way, right? It's not a function, you could call it a relationship. It's x squared plus y squared on b squared equals 1, right? So that's the equation for the whole ellipse. And they're saying from this you should be able to find out what y equals. Okay, just a little note on this diagram here. You should be able to see this in the textbook, but that length from the origin all the way out to the edge of the ellipse there, right, on this major axis, that has length A, okay? And inside the rectangle, right, that would have length X, right, because they've called it XY, and here would have length Y, right? So you can think of these coordinates as lengths inside of this sports stadium, right? Okay, so we have to do a rearrangement. Let's start like this. Y squared on b squared equals 1 minus x squared on a squared. Is it worth going to a common denominator? Probably. So let's go y squared on b squared equals, right? So the denominator is going to have to be a squared, right? That's fine for the x squared. It already had that denominator, right? But how are we going to do that for our 1? We're going to have a squared, aren't we? Right? Because if I'm going to, at the moment, that's the denominator. Right? How am I going to make it an a squared? I have to times that by a squared, therefore have to do it on top as well. Right? Okay. Let's keep going. We're looking to isolate y, so we can move the b squared over here. B squared brackets a squared minus x squared all on a squared. Okay. We could pull out the a squared. I can see from this equation, this part of the equation here, what I need is a b squared on a squared, so that when I square root, right, it'll turn into just a b on a. I can see that where I'm going there in the formula. And I'm going to square root because I've got a y squared. Right, so that's going to get square rooted. This is all going to get square rooted, right? I'll just get rid of that. Apologies about those sound effects, quite irritating. Not sure if they're coming up on the video or not. So I'm going to rewrite this as y squared equals b squared divide a squared, yeah, times a squared minus x squared, right? So it's like I pulled a 1 on a squared out of that expression. Okay, now we're square rooting everything. You can show that in green because there's a square root. There's a square root. So we'll end up with y equals, now technically it's a plus or minus, but we can't have negative lengths, right? Brackets. We don't need those brackets. Right. Square root a squared minus x squared. Okay. Be very careful with square rooting expressions that have plus or minus in them. Okay. This first part, the b squared on a squared, that's the same as this. All right. So whenever you're multiplying or dividing inside a square root, you can go ahead and take the square root, right? That's fine. But let's be very clear on this. The square root of a squared minus x squared is not equal to it's not equal to square root a minus x. Okay, you can't break that up. It's a little bit like, imagine I had this binomial expansion, right? This is not a squared minus b squared, is it? It would be a squared minus 2ab minus b squared. If we thought of this square root as a power, right, of a half, you can see why you can't just do a to the half and b to the half. Right? Okay, so we've got y in the form that the question wanted it. Oakley dokley. Next, show that the seating area, the area equation, now they're telling you what it is. It's 4bx on a times square root a squared minus x squared. It's not too different to what y equals actually. Okay. Now we're talking about the seating area. That's the rectangle. The rectangle here. And the rectangle's length there, or you can think of it along the axis here, would be 2x. And the height of that rectangle would be a y. This would be down here at x and minus y. So there's a distance there of 2 y's. Okay? And that's where my area is coming from. So the area has to be 2 y's, right? 2 times b on a square root a squared minus x squared times 2x's. Or I could just write, sorry, not 2, because 2 times 2 is not 2. 2 times 2 is 4. So I've got the 2 there, multiplied by that 2. I'd have 4bx, all right? So all of this is getting times by 2x on a square root a squared minus x squared. Okay, so that's the second part of the question done. I'm going to slightly rewrite it. I'm going to keep the area expression there, but I'm going to slightly rewrite that. A squared minus x squared to the power of, that's right, you guessed it, a half. Okay, and now I can find the derivative, which I'm guessing is the next bit. So what does it say? Prove that the seating area, there's the area, is maximized when x is a on root 2. So like so many of the questions we do, we need to find a derivative And then we need to set it equal to 0. And what's going to happen, apparently, is we're going to find that x will equal a on square root 2. All right. So how am I going to find the derivative of this function? Well, we could say that this function equals a u times a v, where u is a 4bx on a, therefore a u prime is just 4b on a, and a v here is the square root of a squared minus x squared. Therefore, the derivative of just that bit would be a half a squared minus x squared to the power of minus a half times by minus 2x. And to tidy that up somewhat, what would happen? You've got minus 2x times a half, well that's just minus x, and then you have this square root a squared minus x squared. Okay, probably should have written that over here. Now what I said in class, when I did this question in class, I said you might be starting to get comfortable with product rule or quotient rule, where you don't need to write out equals some function u times some function b. And you're just going to go straight to saying, well, I need the derivative, of this bit times that, and then I need this bit here times the derivative of this part. Okay, and that's fine, right? As long as you get to the right answer. I think maybe for this question it's useful to make a little list for myself, but it is up to you. You don't have to do this work in here, right? If you're starting to feel comfortable enough. Okay, dA on dx will equal, all right, so we need du times v. So v is square root a squared minus x squared plus, although that plus is going to become a minus here, so we'll just write the minus straight in. All right, u 4bx on a times minus x, we've already dealt with the minus, on square root a squared minus x squared. Okay, so really that x there is going to be an x squared, isn't it? All right, maybe write this again. 4b on a square root a squared minus x squared minus, what we got? 4b x squared on a square root a squared minus x squared. Okay, now this next bit I guess is somewhat optional. I'm going to make all this equal to 0, and I'll do it in a certain way, but there's a few different directions you could take with this, right? And what I'm going to do is I like the way that I've got a 4BA here and a 4BA here that look ripe for pulling out of this expression, this equation as a common denominator. But that's really an optional move, okay? So we need to say, okay, we've got square root a squared minus x squared minus, what's left? An x squared. sorry. What are we left with here? An x squared on a square root a squared minus x squared, okay? And it all equals 0. When, so the derivative equals 0 when all of that equals 0. I've taken a common factor out. Therefore, this bit must equal 0, okay? This 4b on a is just a number. Right? I can divide both sides of the equation by that and get rid of it. So we'd be saying, therefore, square root a squared minus x squared. How about I write this? Equals x squared on square root a squared minus x squared. Okay. All right. I could have said this square root minus x squared on that square root equals 0. But what I've done is I've taken that, right, and I have added it to both sides of the equation, right? So I've effectively picked it up and put it over here and added it onto the 0 side. Okay. Now this is prime for a cross multiplication, right? So in one step, I'm going to multiply both sides by the square root of a squared minus x squared, and I'm also going to multiply both sides by 1. So that leaves me with a squared minus x squared equals x squared. All right, let's add an x squared to both sides, so that's coming over here. I have 2x squared equals a squared. Right, therefore, x squared equals a squared on 2. Therefore, x equals plus minus the square root of a squared on 2, which equals a on square root 2. All right? Notice I didn't bother to write the plus or minus. Maybe I should. If I'm in a test, I probably should write that, and then maybe write a little sentence to say we are discarding the negative value because x can't represent a negative length, because negative lengths are not a thing. They do not exist. All right, so this derivative here, it equaled 0. Just need to keep this around for the next part. I think, where have I got enough space on my screen? Let's maybe keep it in this form. All right, so the derivative 4b on a multiplied by square root a squared minus x squared. I'm basically just copying this out again. Minus an x squared on a square root of a squared minus x squared. It all equaled 0. All right. For or when x equaled a on square root 2. So just making a bit of room so we can go and finish off this question. Right. Okay. If we were to draw a sine diagram, the question's telling me it's maximized. I think this is actually quite a difficult sine diagram to think about. The reason for that is if I was to test on either side of this a on root 2, it might get a little bit confusing. If I go down to 0 and try and test that value, I suppose, is that going to work? I guess we could confirm that we would have... No, we can't, because the whole thing will just equal 0 because of that x there. What about in here? That'll equal 0. Oh, we could do it this way. So, sorry, I was looking at the wrong function before. Okay, if I want to test this area, so test in here, find out, is it really positive like it's supposed to be? Because the question is saying that we're going to maximize area here, right? So what could I test? Well, I could test 0, make x as 0. If I make x 0, I need to do that inside of the derivative equation. So that'll be 0. That whole fraction there will be 0. I'd end up with something that was a positive number, assuming that a and b are positive, but they have to be positive, right? A has to be positive, b has to be positive. So that is a valid assumption, and we would be able to show that, a smaller eraser, be able to show that this is indeed positive. Now, if I go all the way out to A to try and test if that's negative, things are going to go pear-shaped, because down here I'm going to be dividing by 0, which is not allowed, right? So that can be a little bit tricky, and it might be a question where if you wanted to really confirm that that was a maximum, the best move to make would be to go to the second derivative and show that the second derivative, right, because we have concave down shape here, the second derivative will always be negative, right? And I did actually look at that in class, and we were able to show that the second derivative would have to be negative for this whole space between 0 and A. All right? We can never have a rectangle, seating area, this rectangle. That rectangle can never be longer than A, because A is the edge of the stadium, the edge of the ellipse. Right? If you're just wondering how I knew that that was my domain that I'm working in here. How did I know that I couldn't have values for x bigger than A? Well, you can see it in this setup, in this diagram. All right. Now, then it says we want to find the percentage of the ground that is occupied by seats. Okay, what does that mean? This is part D. Part D. The percentage of seats. Right. Basically, what that means is we want the area of the rectangle divided by the area of the ellipse times 100 to make it a percent. All right. This is the maximum area, so I need to take A on root 2 and plug it into my area equation so that I know the area of the rectangle. Then I can divide it by the area of the ellipse. The area of the ellipse, they tell us, is A times B times pi. Okay? So, where do we go with this? What's next? Are you thinking? Have you already done it? Right? We need the area of our rectangle where x is a on square root 2. All right. So anytime you see an x, what have we got? 4b times a on square root 2 divide a, and that's going to be multiplied by the square root of a squared. So a squared would be a squared on 2, right? No, I'm making a mistake, sorry. I was doing the x squared. The square root of a squared, right, there's a squared, minus x squared. That's x there. X squared is basically just half of an a squared, all right? So this bit here is the interesting bit at the moment. We've got 4b on a square root 2 divide a times the square root of a squared minus half of an a squared. Right? Well, that's just this, a squared on 2. And if I take the square root of this, look what I'm left with. I'm left with a on square root 2 again, right? So that will reduce down to an a on root 2, okay? And these are multiplied. Okay, let's find some space over here. What's next? Let's put all this together in the one fraction. We've got 4b on a. Up here we'd end up with a squared divided by root 2. Right. Now, this is effectively what's going to happen. The 2 is going to end up on the bottom of that fraction, but we might want to think through that for a minute. So let's write it this way. We've got times a squared divide 2, right? Now, if this is all divided by a, what will that look like? This is all going to be divided by a, yeah? Right, so it's going to look like this. 4b a squared on 2, right? Divided by a, well, that's the same as times by 1 on a. So that equals 4b a squared on 2a, right? That cancels, that equals 1. And this cancels. 4 divided 2 leaves 2. So the area of the rectangle reduces down to 2ab. Okay? So just going to remember that, 2ab. That worked out quite nicely. 2ab is the area of the rectangle. All right, what's the percentage area? Remember, it was rectangle divide ellipse, so it's 2ab divided by pi ab. The book gives you the formula for the ellipse. They're gone, they cancel, and you'll need to times by 100. So you've got 2 divide pi times 100. And that will equal, well, 2/3 is 66%, but that's not quite a third. I don't know, 60-ish%. Let's actually try and do this on a calculator. So if I've just got to remember this, 2 divide pi, okay? So if I delete everything for a minute, go to my calculator, excuse me while it's loading up. I should have had this ready to go, shouldn't I? Okay. How do I clear the screen? I don't know. So 2 divided by pi, right? What does that equal? 63.6% times 100. And this is our answer, right? Don't put all the decimals in. 63.7% approx. And that question is now complete. Thank you for watching.